Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your Sumam. We are continuing fluid kinematics. Let me start with the discussion on fluid kinematics. Fluid kinematics deals with the study of fluid motion without considering the forces which causes the motion. It studies how the fluid flow and how to describe the fluid motion. The topic for today's discussion is flow rate and continuity equation. The equations for the analysis of fluid flow problems are developed from the three basic principles of nature. They are law of conservation of mass, law of conservation of momentum, and law of conservation of energy. The first equation to be developed is continuity equation, which is the equation of flow rate. It is derived based on the conservation of mass, which states that mass can neither be created nor be destroyed. Consider a stream tube in the flow field. What is a stream tube? Stream tube is an imaginary tube which is composed of streamlines passing through a small closed curve. What is a streamline? Streamline is an imaginary line which we can draw in the flow field in such a way that tangent to it at any point gives the direction of the velocity. That means for a streamline is concerned, the component of the velocity in the tangential direction, there is no velocity component in the normal direction. So that is why there is no flow across the streamline. So for a stream tube is concerned, the flow must enter and leave the stream tube only through the end sections. So in this figure, the flow that is enters from the section 1 and leaves from the section 2. So consider a small element of area dA where velocity equal to u. So the volume flow rate that is equal to, that is dq equal to u into dA. Suppose A is the area corresponding to the section 3, then q equal to integral of dq, that is equal to integral of u into dA or u into A. So based on the conservation of mass, the mass inflow that is enters at the section 1 per unit time, that is equal to mass of fluid that flowing out at the section 2 per unit time. Mass of the fluid that is equal to rho into AU. So at the section 1, it is rho 1 into A1 into U1, that is equal to rho 2 into A2 into U2. For incompressible flow, rho is a constant. So we can write A1 U1 equal to A2 U2, that is equal to constant. So if we are applying this for a series of pipes, we can write Q that is equal to Q1 plus Q2, or for incompressible flow, AU that is equal to Q equal to A1 U1 that is corresponding to Q1 plus A2 U2 that is corresponding to Q2. Now let us derive the equation of the continuity in one-dimensional, two-dimensional and three-dimensional flow. Let us start with the derivation of continuity equation for three-dimensional flow using Cartesian coordinates. So consider a controlled volume A, B, C, D, E, F, G, H within the flow field in the form of a rectangular prism having sides delta x, delta y and delta z in x, y and z direction respectively. So since it is a three-dimensional flow, the velocity has the component u in x direction and v in y direction and w in z direction. Mass inflow per unit time in x direction through the phase ABCD, that is equal to rho u into delta y into delta z. So delta y into delta z indicates the area of this phase ABCD. Since density and velocity that is varying in x direction, then mass outflow in x direction per unit time through the phase EFGH, that is equal to rho u plus dou by dou x of rho u into delta x into delta y into delta z. So net mass outflow in x direction per unit time, that is equal to difference of these two, that is rho u into delta y into delta z minus rho u plus dou by dou x of rho u into delta x into delta y delta z, that is equal to minus dou by dou x of rho u into delta x delta y into delta z. Similarly, we can consider net outflow per unit time in y direction and in z direction. So net outflow in unit time in y direction equal to minus dou by dou y of rho v into delta x into delta y into delta z. Similarly, net outflow in unit time in z direction equal to minus dou by dou z of rho w into delta x into delta y into delta z. Total net mass outflow per unit time, that is equal to summing the net outflow in x direction and y direction and z direction. So that is equal to minus dou by dou x of rho u into delta x delta y delta z plus dou by dou y of rho v into delta x delta y delta z plus dou by dou z of rho w into delta x delta y delta z. Now change of mass within this control volume per unit time, that is equal to dm by dt, that is equal to dou by dou t of rho into delta x delta y delta z. So delta x delta y delta z is the volume of this element multiplied with rho gives the mass. So the change of mass within this control volume, that is equal to net mass outflow in unit time. So that means 1 equal to 2. So if we are equating these two equations, then the final expression equal to dou by dou x of rho u into delta x delta y delta z plus dou by dou y of rho v into delta x delta y delta z plus dou by dou z of rho w into delta x delta y delta z plus the change of mass within the control volume, that is dou by dou t of rho into delta x delta y delta z equal to 0. So if you are eliminating the common terms, that is delta x delta y delta z is common, then the final expression is dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w plus dou rho by dou t, that is equal to 0. So this equation holds for every point in the fluid flow, whether steady or unsteady, compressible or incompressible flow. So this equation is a general equation. This we can apply for any type of flow, that is steady or unsteady, compressible or incompressible. If the flow is incompressible, density is constant. So from this equation, the density can be eliminated. So after eliminating the value of density, this equation can be rewritten as dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. So this equation can apply for a three-dimensional flow for incompressible fluid. Suppose the flow is two-dimensional, then we have the velocity component in x and y direction only. So our expression is dou u by dou x plus dou v by dou y, that is equal to 0. If the flow is one-dimensional, then it is dou u by dou x equal to 0. So if you are considering the cross-sectional area, then this equation leads to AV equal to constant or A1 V1 equal to A2 V2. So this can be explained by means of this figure. So A1 and V1 is the cross-sectional area and the velocity at the section 1, and A2 and V2 are the cross-sectional area and the velocity at the section 2. So A1 V1 equal to A2 V2, that is the content equation which we have derived earlier. Let us discuss the content equation by solving a problem. So in this problem, velocity vector is given as v equal to ui plus vj plus wk. So we have to check the possibility of steady incompressible flow. So if this flow is existing, then we have to find out the velocity and acceleration of the fluid particle at the point 1, 3, 3 corresponding to xyz. So this velocity vector represents three-dimensional flow. The velocity component u, that is given as 4x cube, and the velocity component v, that is given as minus 10x square y, and velocity component w, that is given as minus 2x square z. In order to check the possibility of steady incompressible flow, then continuity equation must be satisfied. So for a three-dimensional flow of incompressible fluid, the continuity equation is dou u by dou x plus dou v by dou y plus dou w by dou z, that is equal to 0. So if you are differentiating this velocity component in x, y, z directions, then dou u by dou x equal to 12x square, whereas dou u by dou y and dou u by dou z, that is equal to 0. Similarly, dou v by dou x is equal to minus 20xy, whereas dou v by dou y, that is equal to minus 10x square, dou v by dou z and dou v by dou t, that is equal to 0. Similarly, we can differentiate w with respect to x, y and z and t. So if you are substituting for dou u by dou x plus dou v by dou y plus dou w by dou z as 12x square minus 10x square minus 2x square, then this equation is satisfied, or it is equal to 0. So that means it is a possible case of steady incompressible flow. So next stage we have to calculate the velocity and acceleration of the fluid particle at 1, 3, 3. So velocity vector at the point 1, 3, 3 can be obtained by calculating u and v and w at the point 1, 3, 3. So u, that is equal to 4x cube. So if you are substituting x equal to 1, the u equal to 4. Similarly, v equal to minus 10x square y. So if you are substituting the value of x equal to 1 and y equal to 3, the value of v equal to minus 30. Similarly, the value of w equal to minus 6. So our expression equal to v equal to ui plus vj plus wk. So if you are substituting, the velocity vector equal to 4i minus 30j minus 6k. And velocity equal to root of u square plus v square plus w square, that is obtained as 29.666 units. The relative position of the fluid particle thus not fixed, and it varies from time to time. So we have to find out the total change in velocity with respect to space and time. So the acceleration, that is equal to the summation of convective acceleration and local acceleration. So the expression for acceleration in x direction, that is equal to the convective acceleration plus local acceleration. But it is given that the flow is steady. So that means there is no local acceleration at all. So if you are substituting for ax as u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z, then ax equal to 48x raised to 5. Similarly, ay, that is equal to dv by dt, that is equal to u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z plus dou v by dou t, that is equal to 20x raised to 4y. Similarly, az equal to u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z plus dou w by dou t. Correspondingly, you can substitute the velocity component and differential of that, then az, that is obtained as minus 12x raised to 4 z. But the value of x, y, z is given as 1, 3, 3. So if you are substituting the corresponding values of x, y, z for ax, ay and az, then ax obtained as 48 unit and ay, that is equal to 60 units, and az, that is equal to minus 36 units. So a, that is equal to axi plus ayj plus azk, or it can be written as 48i plus 60j minus 36k, or acceleration equal to root of ax square plus ay square plus az square, that is equal to 84.85 units. All of you can solve the problem by your own and verify the answers. The next problem we are going to discuss is the application of continuity equation for a series of pipes. So the figure shows that water flows from A to D and E through a series of pipeline. The data to be determined for the pipe segment AB as Q1 and V1, whereas for the pipe BC we have to determine the discharge, and for the pipe CD we have to get the value of discharge and diameter of this pipe, Similarly, for this pipe segment CE, we have to get the value of discharge and velocity. Now, based on this figure, we can write Q1 equal to Q2 and Q2 that is equal to Q3 plus Q4. But it is given that Q3 equal to 2Q4 or Q4 equal to Q3 by 2. So if you are taking Q4 equal to Q3 by 2, then we can write Q2 as 1.5 Q3. Now, in this figure, it is given that for the pipe segment BC, velocity is given and diameter is given. So the expression for discharge that is equal to Q equal to AV. So A can be calculated here and velocity is available. So discharge through the pipe segment BC can be calculated. So that is equal to 8.839 into 10 raised to minus 3 meter cube per second. So Q1 equal to Q2. So Q1 that is also equal to 8.839 into 10 raised to minus 3 meter cube per second. And Q equal to AV. So based on this discharge, we can calculate velocity because area is known here. Diameter of this pipe segment AB that is given as 50 mm. So we can calculate area. Correspondingly, we can calculate the velocity as 4.27 meter per second. And for the pipe segment CD, it is given that Q2 that is equal to 1.5 Q3. So Q2 is known. So Q3 can be calculated as 5.893 into 10 raised to minus 3 meter cube per second. So discharge is known, velocity is available. So we can calculate the area of cross section as A3 equal to Q3 by V3, from which we can calculate D3. So D3 equal to 70.7 mm. Now for pipe segment CE, Q4 equal to Q3 by 2. So Q4 can be written as 2.947 into 10 raised to minus 3 meter cube per second. Since area is available here because diameter is given, so V4 is calculated as Q4 divided by A4, that is equal to 4.17 meter per second. So based on the continuity equation, that is Q equal to AV, we are able to calculate all the unknown parameters. So this problem also you can work out by your own and verify the answers. Now the session comes to an end. For the time being it is enough. Thank you.